So welcome to today's lecture recap. And today we're going to move from talking about oscillators, individual objects subject to restoring forces, to talking about systems where you have basically effectively many of these objects coupled together. And this is going to mean we're going to be going from the physics of oscillations to the physics of waves. So just a quick review of what we talked about last time. We understood that if you have an oscillator, then sometimes there are additional forces on that oscillator. So in the left-hand case here, we were talking about situations where you have drag forces. These end up taking some of the energy that you have in your oscillation and then converting it into like the energy of motion of the fluid that you're surrounded by, and eventually just into heat. And so these drag forces basically take energy out of your oscillating system and the amplitude decreases eventually to zero. We also talked about forces that you can apply to oscillating systems that are time dependent. These forces actually can add energy to the system. And so we saw that the oscillating force can drive the oscillation. And we understood this phenomenon of resonance, where if you match the frequency that you're driving the system with to the natural frequency that the system wants to oscillate with, then you get a very large amplitude. Okay, so the main reason we're talking about these oscillators is not necessarily because we're so interested in masses on springs. They have many applications thinking about individual oscillators, but the main reason that we want to develop this mathematics of oscillations is because this comes into our understanding of waves, and waves are almost universally important in physics. So we have sound waves, light waves, vibrational waves that travel through solid materials. More fundamentally, we have these gravitational waves. And when you really understand particle physics, so when people are trying to understand physics and nature at the most fundamental level, it's entirely in terms of these basic kinds of waves and applying the rules of quantum mechanics to the study of waves. That actually gives us an understanding of what particles are. And that applies to photons and electrons and every other kind of particle. So waves are really, really fundamental in physics. And so today I want to understand, starting from what we know about oscillators, understand how waves arise. So I want to start with a simple situation that's shown here, where you have a whole bunch of coupled oscillators. And so this is a bunch of masses connected by springs. And this thing is going to be kind of like a model for solid materials or more complicated materials where you have many different parts that are connected together. But let's just imagine this simple situation right now where you have the masses, they're connected by springs, and I want to imagine we displace one of those things. So I want to imagine the original situation is that all of these things are in equilibrium, but now we maybe pull down the leftmost spring here and release it, and then understand what will happen. So there's a couple of things here that are different from when we just had a single oscillator. Okay, so the first one is that when I pull this down, it's going to, number one, it'll exert a force on the next oscillator. And that one can also move. And so this first oscillator, as I pull it down, that feels a restoring force from, say, this spring. It also pulls down the second one, and then that second one acts with some restoring force on the first one additionally. So if I allow this thing to evolve with time now, then what's going to happen is that second one is going to get pulled down a little bit. And then it will go ahead and pull on the third one. And now you notice the first one is oscillating back up. And the third one now is oscillating down, and it pulls on the fourth one. And so instead of just a single thing oscillating, we've got this disturbance that actually propagates through along the chain. And then thinking about the first oscillator, well, it won't keep oscillating forever because obviously some of its energy of oscillation is going into the second oscillator, and then the third oscillator, and then the fourth one. And so as that disturbance propagates along the chain, we expect that the original oscillator on the left will kind of settle back down to its equilibrium position. Okay, and so this is the origin of what we would call a propagating wave. This is a simple kind of wave pulse that has a finite extent along the chain. So there's just like a few, in my picture, there's just a few of the oscillators that are displaced at any time, and those few move down the chain, or the oscillators don't move down to the chain, but the disturbance moves down the chain. Okay, so let's actually see that in action. I want to show you a demo that I recorded here. Oh, actually, no, I don't. For these recordings, I just want to click on it. Sorry, let's do that again. Okay, just share my screen, and then I just actually click on this. There we go, automatic. Okay, so in this simulation, we have a bunch of masses, and they're all coupled together by springs. And I've set up an initial condition where the first mass is displaced downward. And then we're going to start it, and we'll see what happens. Okay, and so as you can see, let's start again. After I let it go, the first one, if we watch the first one, it oscillates and then kind of dies out. But then you can see that it transfers its energy to the other oscillators down the chain. So the first one kind of drives the oscillation of the second one, and that drives the third one, and so forth. And so you get something that basically looks like a wave traveling down the set of masses and springs. And let's just have a look at that one more time in super slow motion. Okay, that's way too slow. Let's go a little faster. Okay, here we go. And so you can see the disturbance propagating down the chain. And then the original spring, the original mass, it has basically stopped oscillating after a while. And in this case, you have a wall on the right-hand side, and so the thing reflects backwards and originally starts exciting those masses on the left again. All right. Let's close that one up. Grab my slides again. Okay, so that was what happens if we take a single pulse and we move it along. Sorry, a little bit loud. We take a single oscillator, we displace it, and we let it go. And then what we saw was we get a pulse that moves along the chain. The other thing we could imagine doing is actually driving the first oscillator, meaning that we apply some periodic force so that it moves up and down and up and down and up and down. We keep doing that. And then again, well, we're transferring energy into that oscillator by making it move, but then it transfers energy into the remaining oscillator. So it drives the second one, and the second one drives the third one, and the third one drives the fourth one. But there's a little bit of a lag. And so what you find is then you get basically some periodic wave that keeps traveling down the chain. And so it looks like a sinusoidal function, even as a function of x at any time. And then the time dependence of any single one of those oscillators is also some sinusoidal function. So the kind of wave that we're showing in this case, that's what's called a transverse wave. And it's because the motion of the disturbance is in one direction, and the motion of the oscillators is in the perpendicular direction, up and down. Okay, so the motion of the disturbance, of course, none of the oscillators are actually moving in that direction. It's just the wave crests, or if I have a single pulse, that's the direction that the pulse is moving. And then in a transverse wave, the actual objects that are oscillating, they're moving in a direction that's perpendicular to that motion of the pulse. Okay, so I wanted to kind of distinguish that from the other alternative, which is what we call a longitudinal wave. And so that would be if we actually have an oscillation in the same direction that the pulse is going. So you can imagine if I start shaking the leftmost mass left and right, then as we let time pass, that's going to cause the other masses to start shaking left and right. And so that disturbance again is going to propagate along the chain, and we get this sort of oscillation. So this is my low-tech animation of what a longitudinal wave would look like. Okay, and let me just show you that in a slightly higher tech version with a simulation. Okay, so this time I'm going to simulate a longitudinal wave. And to do that, instead of displacing this first mass in the upward or downward direction, I'm actually going to displace it to the left. So I compress that spring on the left and I stretch the second spring. And so now if I let things go, we're still on super slow motion here, then you see that the wave is traveling to the right and the disturbance propagates from right to left, and that first mass eventually settles down until the wave comes back and then excites it again. Let's see that again, but this time at regular speed. So here we go. Okay, and so you see it moving right down the chain of oscillators. Okay, so there it was. How do I get out of this? There we go. There's my slides again. I think during the video I said the disturbance was moving from right to left, but obviously it was going from left to right, I think, on my screen at least. So, so that was something like waves in a very simple situation where you simply have a bunch of masses and they're connected together in some way. In that picture, I had them connected together by springs. Okay, but many physical systems are more or less behaving in that way. So even though you don't have actual little springs in something like a solid, what you do have is many different parts. And you have that if you displace any one of those parts, say to the left, there would be restoring forces. So if you think of some part of a solid, let's imagine you have a marshmallow, you push on one part of the marshmallow, well then the rest of the marshmallow is going to push back on that part. Or if you imagine a part in the middle of the marshmallow and you move that up a little bit somehow, then what's going to happen is the rest of the marshmallow is going to push it down again. So many physical systems, most physical systems actually have this situation, have this behavior of giving restoring forces for any part of the system that gets displaced. And so we can go from this basic picture of masses and springs and see that as a model for a real material. So it's simplest actually first to think about a one-dimensional kind of material. And so the most direct application of our masses and springs model would be to understand the physics of just like a stretched string. Could be a guitar string or a violin string or any other kind of a string or a cable that would have some tension on it. Okay, like that old homework question with the gold and the platinum wire. And so what happens here is that if I imagine the equilibrium position of the string, which is just stretched straight out, and now I displace a little portion of the string, like that one. So I move that up a little bit. Then we can try to understand what are the forces now on this part of the string that I displaced. Okay, so we're imagining like a certain length of string there. Previously, it had forces going to the left and going to the right. Those balanced out. The net force was 0. But when I move the string up a little bit, now the tension forces have a downward component to them. And so what you see is that the net force from this tension is pointing in the downward direction. So when I displace it up, the net tension force points downward. If I displaced it down, there would be a net force pointing upward. And so you see that we have this restoring force. And then we also have the force from this on the neighboring part of the string. And so if I displace this part upwards, it's also pulling upward on the neighboring part. And so it's very, very similar to this situation with the masses connected together. And so we're going to get the same kind of phenomenon. If you have a stretched string and you start displacing one end of it, you're going to see pulses that travel down the string. And I've got a nice little simulation of that here. So in this simulation, we have a stretched string, and I can control the motion of the left side with this wrench by moving it up and down. And so let's see what happens if I move the wrench up and down. And actually, we've got it set on slow motion. So you can see that this disturbance that I've created travels slowly from left to right. And similarly, if I move it down and then up again, then we've got kind of a wave traveling along the string from left to right. And you notice that the left part of the string, once that wave is gone, in this case, it doesn't come back. And so if I pause the video this time, we can have a look at what happens at various times. And so you see at any given time, then there's a particular shape of the wave on my string. And then I could wait until some later time and I could pause it again. And now there's a different shape. So we're about to talk about how we would mathematically describe waves on a string. And what's important is that there's going to be a particular function that we could plot at every different time. So we have one function of the position x for every time, and that's going to give us some mathematical function of two different variables. Before we go here, I'm going to actually show you a different kind of a wave where instead of just making a pulse, I could actually continue to drive the left side of the string. So let's go to normal speed here, and we're just going to move it up and down. And then what you see is your classic kind of sinusoidal wave. Okay, in this case, the shape of the wave in space is actually a sine function. But as we saw in the last example, that's not necessarily true in a simple wave, in a simple kind of situation where I maybe only move it up and down once, then you see the shape of the wave can be something completely different. All right. So, okay, so that was a nice example where depending on what I do to the left side of the string, then we see that you have waves traveling to the right, and they could look like a single pulse if I just move the wrench up and down once, or they could look like a sinusoidal wave that's continuously moving to the right if I keep driving the left end of the string up and down. And so I was talking about the mathematical description of all that. So we might want to describe precisely what the string is doing at all of the possible times. And so what we need there turns out to be a function of two variables. One of the variables is position. The other variable is time. So in order to motivate that, I want you to think about how you would describe the shape of the string at one particular time. And so that would be like taking a picture of the string and then looking at, you could take a picture of it, it would look something like this. And then mathematically what you would need in order to describe that would just be a function of the position x along the string. And the function would tell you how much is the string displaced at a given position. Okay, so this would be some function. I'm going to call that d of x. Okay. Now if you wait and you let this wave propagate along the string and you take a picture at the next time, let's say t equals 1 second, well, then there would be a different function. So I'm calling it d of x again, but this d of x is different than the previous one because you see now the pulse is at a different location. In my simple example here, the thing is remaining the same shape, but in general, that pulse might spread out or do something else as it travels along. Okay. And so you see that in order to completely describe this wave, what you would need is like one function for each possible time. Okay, and the time is really a continuous variable. So mathematically, you need something where you could plug in a certain time t equals 0, 1, 1.5, 2, whatever you want, and then you still have a function of the position. And so this is like a function of two variables. Okay. Let me just do a quick example of what I mean by this function of two variables, and then we're going to see a lot more examples next time. So say we have this function sine of x plus t. So this is a function that we could plug in an x and we could plug in a t, and then it gives us a number out of that. And so what I mean by the function evaluated at time equals 0 is that if I plugged in t equals 0 into this, then what's left is just a function of x. Okay, and that's something we could plot. And what that picture would show, what that graph would show, is what the string looks like at that given time t equals 0. Okay, so that's some shape. But the other thing we could do, that's interesting is to set x equals 0. And then we would get a function of time. Okay, and in this example happens to be the same function, but this won't always be true. So I could have something more complicated than this function where I would get a different function. So what would this function mean, the sine of t? That would mean that I look at the string at some particular position, or actually I'm looking at it right here, and I follow what is the displacement doing as a function of time. Okay, so instead of looking at the entire string at one time and kind of plotting a graph of what it looks like, what I can do is just look at let's say there's a bead on this string at this location, that's going to move up and down with time. And I could also make a graph of that up and down motion. And in this simple example, that's also some kind of a sine function. So we can describe that first kind of graph, the one that I've shown on this slide here. So here I've got a bunch of examples of what I'd call a snapshot graph. That's plugging in some specific time and then looking at the function of x. So those are snapshot graphs because it's like taking a picture of the string. And then the other kind of graph I was talking about is what I'd call a history graph. That's the behavior as a function of time of one point on the string. Okay, so here is an example. This is a really important kind of question, being able to go back and forth between the snapshot graph and the history graph. And so I want you to definitely take some time to think through this one, because this is a really important kind of question that you're going to be seeing. So the setup here is that I have a wave that has this particular kind of triangular shape where it's steeper here and it's less steep here. And what I'm going to do, what this graph is showing, is the snapshot at time equals 0. Okay, so at time equals 0, the part of the string between 0 centimeters and 1 centimeter is stretched, and the rest of it is flat. And now what I want you to think about, what would the graph of displacement versus time be if I were to watch the motion of that green dot? You can imagine that's a bead that's attached to the string. What would the displacement versus time graph look like for that green dot? Okay, so take a little bit of time to think about that, and then we're going to talk about it. Okay, so what do we do? What we want to do here is actually visualize this thing. So you've got a wave moving along. The picture that's shown is time equals 0. And so at time equals 0, you see that the displacement is 0. So this green bead is just sitting at x equals 0. And then you see that at some later time, then this wave will move along and hit the place where the green bead is. So what we should expect is that in our graph of displacement versus time, the displacement should be 0 at time 0 and all of the times before time 0. So either answer C or answer D would be consistent with that. And then at some later time, when this wave arrives at our location, then we're going to expect that the displacement goes up and then goes down again. So now we have to decide between C and D. And in the lecture class, it was equally split between these two things. So the difference between C and D is that in C, what it shows is that the bead goes up in a relatively short amount of time. It goes up quickly and then comes down in a longer amount of time. In option D, it takes a longer time for the bead to go up and then a shorter time for it to fall back down. Let's compare that with what actually happens. So in the actual situation, you have this steep part of the wave pulse, and that ends up hitting the green bead first. And so basically the green bead, it sees the steep part and therefore moves up relatively quickly. And then as the wave continues to travel along, the green bead comes back down, but that will be at a slower rate. And so in this case, the answer turns out to be C. The shape of the snapshot graph actually looks like the shape of this history graph is actually kind of reversed from the shape of the snapshot graph. And that's because the wave is moving from left to the right. Let me show you that in the simulation. So, okay, so I'm going to try to create a wave with the shape that we saw in the clicker question. And we're going to watch what happens to one of these green balls as the wave goes by. So let's try that. Okay, so there we go. So we've got a shape more or less like the one in the question. It rises steeply on the right, and then it comes down more gradually on the left. And what I want to do is watch this green ball right here. Let's say that is the string at position x equals 2. And we're going to imagine that we're going to make a graph of the height of that ball as a function of time. That's what the question is asking. Okay, and so let's say this is time 0. And so you notice that originally the height is 0. And now we're going to let it go forward. So it goes up quickly and then down slowly. And so as a function of time, then you'd have it be flat, and then it would rise steeply, and then it would come back down more gradually. Okay. So just to make sure that this is kind of absolutely clear, so the answer here is C. I want to just do one more explanation of that, because I know this is something that I always get a lot of questions about. So in this picture, what I'm actually going to do is draw the graph in real time. And so let's look at the top picture. This is going to be my string, and here's my graph that I'm making. And so what I notice is, let's say time equals 0 right here. And so I plot that the displacement of this ball is 0. And then at a slightly later time, the wave has moved along. And again, I plot that the displacement is 0. Slightly later time, that's when the wave actually first hits the ball. And at that time, the displacement is still 0. But then now at a slightly later time, okay, then the ball has moved up to that position. And so then I would plot that it's halfway up. And now slightly later than that, the ball's right at the top. And so I would plot that. And then again, comes down. And it takes a little longer for it to come down than it did on the way up. And then I'll plot that one. And so at some point we've reached the end, and then all the times after that I get 0 again. And so then I get this graph. It goes up relatively quickly, and then it comes down more gradually. All right, so hopefully that was relatively clear. We're going to give you more practice on that in the upcoming homework, I think. our final homework of the year. And so in the last part of the class, what I want to do is just now kind of talk about how this all generalizes to real three-dimensional materials. So we did first a very simple example where we had masses connected by springs. We said that was very similar to the physics of a stretched string, so like a one-dimensional object. In more complicated situations, we normally have three-dimensional objects. And so there, let's start by talking about solids. When you have a solid, basically every atom is almost like a little oscillator. So every atom is fixed in place in a solid, and that means that if we displace it to the left, there will be some kind of restoring force that brings it back to the right. If I displace it to the right, there'll be a restoring force that brings it back to the left. And so that's why, in a solid, you can have vibrations of the molecules and they don't just sort of move all over the place. And we already talked about these vibrations in the context of thermodynamics, that when you add heat to a solid, basically the molecules are vibrating. And the reason that they're just vibrating in place is basically because of these restoring forces. So it's very similar to lots and lots of little masses coupled together by a whole bunch of little springs. So this kind of gives you a nice model for the behavior of a solid. Okay, and as I was mentioning, when we think about just the thermal energy of a solid, that corresponds to all these individual vibrations, and those are basically random. So the vibrations of nearby molecules might be in different directions. Okay, so that's like a thermal oscillations in a solid. It's happening at the microscopic level. But if you look at large groups of molecules, they're not really moving together in any way. So what distinguishes something like a wave or a vibration in a solid from that thermal motion is that in a wave or a vibration, lots and lots of nearby molecules, they're all on average moving in the same direction. So suppose you have a brick, and if you were to hit the brick with the hammer, and don't worry that it's a brick, so it doesn't get hurt by the hammer. So you hit it with a hammer. What happens is the brick starts vibrating, and if we thought about that at a molecular level, then that would be like entire layers of the brick would be sort of initially you hit it with a hammer, and so a large number of molecules move downward a little bit together, and then they push on the next layer of the brick, and that layer pushes back. And so that first layer kind of oscillates down and then back up, and then the second layer oscillates down and up, and it can keep oscillating a little bit. So you have kind of large collections of molecules moving together, and then the disturbance propagates all the way down to the bottom. And you'll notice in that example, it's a longitudinal wave, just because I set it up by a compression of the material. And so that's the kind of wave that would represent a sound wave in a solid. Okay, so in this case, it's just an actual vibration that we cause by hitting with a hammer. But sound waves work the same way. It's just a more gentle vibration. If I start talking, and then the air pressure, it turns out, increases at the surface of the brick, and that forces some of the molecules at the surface of the brick down a little bit, just a tiny amount, and then they exert forces on the next level of molecules. And so you get these longitudinal oscillations. So various kinds of vibrations or sound waves you could understand as longitudinal waves in a solid. But of course, you could also have the more transverse waves, more similar to the waves on the string. And so that's what this picture is showing. Turns out when you have an earthquake, which is like a very large wave that happens at large scales in the crust of the earth, well, then you can have waves that are like sound waves. So you can have these compression waves, and that's one part of the earthquake. That turns out to travel a little bit faster, and those are the first waves that will hit you when you feel an earthquake. But then you also have transverse waves, and so that would be just an up and down motion of the large collections of molecules in your solid, whereas the wave is traveling, in this case, horizontally. So you can have either longitudinal waves or transverse waves when you have waves in solids. Okay. That is what I wanted to say about that. Next, we can talk about waves in fluids. And so that would cover liquids and gases. And I guess the main difference there is that at the level of individual molecules, the gas or the liquid, you're not feeling these same restoring forces that you would have in a solid. So you know that in gases and liquids, the molecules are kind of free to move around relative to one another. Okay, and so you might think, okay, well, this physics of oscillations is not really going to be relevant in that case. But we've already seen examples of how you can get an oscillator just starting with some gases. So for example, that situation with a piston in a cylinder, we've already understood that if you just place it downwards, you get a little bit higher pressure, and then that pushes back on the piston, and then that will go up, and you can end up getting an oscillation that way. And so actually, when we think about sound waves and oscillations in gases, it's exactly that picture, except instead of a piston, it's just like a layer of air. So let me try to show you that. So what is a sound wave microscopically? You could imagine that your air molecules are more or less uniformly distributed. And if you don't have any waves propagating through, then that would be a uniform density or a uniform pressure throughout your fluid. So this argument is going to apply both for air and for water. So that's why both of those I would call fluids. Let's understand what happens then if you displace some of these air molecules. Okay, so let's say I somehow move the air molecules to the right a little bit. Okay, so this is basically what happens when I create a sound. I clap my hands or something, and that displaces the air in some way. And so what happens is that you create a certain region of your air that would have a higher density. So because of this displacement of molecules, they maybe are actually colliding with something, and then temporarily the density is slightly higher here. And so by the ideal gas law, that region also has a slightly higher pressure. And so what's going to happen is that this region, the molecules in this region, will then push on the molecules in the neighboring region and exert a force on that neighboring region. Okay, so like a speaker is basically just pushing air molecules. It's moving back and forth. There's actually a physical object moving back and forth. It's pushing the air molecules, creating a region of higher pressure. And then let's have a look at this set of molecules in the box here. And so what we notice is that on the left-hand side, you've got higher pressure because you have a higher density of air molecules. On the right side, you've got lower pressure because you've got a lower density of air molecules. And so if I think of this whole layer of air molecules as a part of my system, it has a certain mass and it has a net force on it that is to the right. And so those air molecules are then going to get forced into this region, which currently has a low density, and they're moving away from the region that currently has a high density. And so then as a function of time, the places where you used to have a high density are next going to have a low density, and the places where you had a low density are going to have a high density. And so you end up getting oscillations, and it's not oscillations, it's kind of like a collective oscillation where all these air molecules are moving together. They're also moving around randomly, but on average, the ones in this box are going to be moving to the right, and then they move to the left, and so forth. Okay, so that is your basic picture of a sound wave. And then finally, I have a video to show you this. And so there's actually a way to visualize the differences in density in the air. So you can watch the whole video if you want to understand how these images that I'm about to show you are produced. But what you're going to see is various kinds of sound waves, and you'll actually be able to see where in the air is the pressure greater and where is it less. Okay, and so it's really short.
Aerodynamic flow. And sound, well, that's just another change in air density, a traveling compression wave. So Schlieren visualization, along with a high-speed camera, can be used to see it as well.
Okay, so just to pause that for a second, what you see is this method, which they call Schlieren visualization, is just showing this is a darker region here, this is a lighter region here, and that means that it's more dense here and less dense here. And so you can see a sound wave going out from the speaker. You can see these different regions, and then if I let that play,
here's a book landing on a table. The end of a towel being snapped. A firecracker. An AK-47. And of course, a clap.
Okay, so actually I just wanted to show you the speaker example one more time, and I'll do that at slow motion so we can really see it. So okay, here we go. So this is the model.
Traveling
and then
with a high speed.
Okay, so here is so you can really see that wave propagating outward from the speaker. And it's just regions of high and low pressure. All right, so that is, I believe, all we had for today. Next time, we're going to get more into the mathematics of waves and how to understand what would specifically this function d of x and t look like for simple situations like sinusoidal waves traveling down a string and so forth. So have a good the rest of your day, and we'll see you on Friday. I think it's Wednesday today. Bye-bye.